Well, good evening, everybody, and welcome to our Edinburgh Napier Professorial series of lectures. And it's a very exciting lecture, not just because of our speaker we have tonight, but because we had suspended these lectures for the best part of 3 years. Indeed, the last lecture professorial was done by Peter Barlow, in immunology. He was talking about viruses and flu and pandemics at that time. And then since then, we've had a 3-year hiatus. So it's absolutely wonderful to be back and to see so many people who've come and joined us today. Now, I'm Andrea Nolan. I'm the principal of Edinburgh Napier University, and I've been here nearly 10 years. And as a leader, you make some good decisions, you make some bad decisions. One of my best decisions I made 2 weeks after I arrived was appointing Gary as head of the school of what was then life sciences, well, a bit broader. And Gary has had a very distinguished career. He did his undergraduate degree at Stirling University and a master's. He then did a PhD at Edinburgh Napier University and moved to the University of Edinburgh to start his postdoctoral career with the MRC unit there. He's had a very distinguished career and leads nanosafety research at the university. And I'm not going to tell you what nanosafety is. I know Gary will demonstrate that through his lecture. I just know it means things are very small and how they get into your body and the damage that they could potentially do. Gary currently chairs the Scottish Institute for Policing Research Board of Governance and the Edinburgh Exchange Initiative through the Edinburgh International Conference Centre. He's been an independent scientific advisor to UK government for over the last decade, with previous membership of UK Hazardous Substances Advisory Committee, DEFRA, and currently the Food Standards Agency Committee on Toxicity of Chemicals in Food, Consumer Products and the Environment. And he's a member of many specialist registers from the Food Standards Agency, DEFRA, and the Office for Product Safety and Standards. You can see where this is all going around safety. So I'm very pleased that Gary is going to speak to us to Toxicology, a journey into the Valley of Death. I did ask him if there should be a rating on this, but I'm assured not. And just brought my phone to remind you, please, to turn them to silent if you have phones. And we're not planning a fire drill. If there is, the fire drill bell does go off, we go basically out of the room, down the stairs and out to the front, exactly the way you come in. Enough of introductions, and over to you, Gary.
Thanks, Andrea. Good evening, everyone. Thank you for those kind words, Andrea, and introductions. I don't know if I'm more nervous now standing in front of this audience or standing in front of you being interviewed for the role of head of school back in 2012. But thank you, everyone, for coming out tonight to hear about my journey through the Valley of Death as a toxicologist. What I wanted to do is share a bit of my interests and my passions. And for those that know me quite well, people know that I've got an interest in history, and hence the picture on my slides. It's a bit of a pop quiz. Does anyone know what that picture is of? Yes? Charge of the Light Brigade. Yes. So that's the journey through the Valley of Death. It's not a negative metaphor. I'm not trying to say that an academic journey is something like the charge through the Valley of Death. But what I wanted to really share with you today is that by looking at history, we can learn from it. And it's actually history which informs our forward thinking. And that was written and made sort of famous, I would say, by Lord Alfred Tennyson. So he wrote the poem, which really sparked the words about that journey, that tragic incident took place. Now, the other great literary should I say scholars, but agents in the world have come up with other titles and other words that are really profound. And I think if anyone recognises this, people have written about the history books on the shelf are always repeating themselves. Does everyone know who said that? ABBA. So another great literary world. So Waterloo, a different war this time, but this was our focus here. And for tonight's lecture, I want to just keep on reflecting on how I've learned from history and how I see history repeating itself. But to start the journey through the Valley of Death, it starts at the beginning. So please bear with me for the first couple of slides. It's me just indulging myself about how I got to here today. And I do apologise to those in the audience that might be a bit embarrassed by some of these slides. So the journey begins with me. I am a student at Alva Academy. I was head boy, trying to keep up with the rather handsome man to the left of me who was the deputy head boy. And at this time, I thought I was going to try and sport something quite interesting in relation to hairdos. And at that point, Philip Schofield was the man of the hour. And I asked my barber for a Philip Schofield hairdo. Unfortunately, that did not work out for me. From Alva, I finished my schooling and I went to University of Stirling, as Andrea has just highlighted. I was the first in my family to go to university, and it was quite daunting. I didn't go too far along the road. I went to the University of Stirling, and I stayed at home. And that brought some challenges for me. But at this time, when I moved to Stirling, I was a student who was first in family and didn't have access to the learning and support that maybe other people have. And at that time, Stirling perhaps was less aware of the needs of students coming from backgrounds such as mine, and therefore I struggled a lot in my first year to actually understand how to engage with information, how to find out how to study, and how to get support. And my parents, God love them, tried to support me through the first year of my studies by using something called the Pear's Encyclopedia to help me through my chemistry. We got there. It was a tricky first year. I persevered. I started to enjoy student life. And I graduated, which was really important. And it was a very proud day. And of course, this was the day before the GoPro, so my father isn't in the picture. He's the one taking the photograph, but I'm here with my mum and my brother. My brother can't be here tonight because he's unfortunately having to work. So once I finished at Stirling, I decided my molecular biology degree was of an interest, but maybe not where my passion was. And I went to Napier. And this was the first person I met at Napier, Dr. Proudfoot, Lorna, who's in the audience. And Lorna met me and my friend to give me a tour of the university. And that was quite a big thing for me because this was a welcoming environment. And this month we recognise National Women's Day. And I want to share with you some of the women that have really influenced my career to date. I met Anna, so Dr. Anna Baker, and she was Cloucher at the time, and Dr. Vicky Stone. These lecturers were fantastic. They were toxicologists or teaching toxicology, and the three very, very important women there actually inspired me to stay on and do science because it wasn't a career path that I thought I was going to follow. There was a fourth lady I met in Napier as well, and this was a member of the technical staff, and of course that encouraged me to stay as well, but we'll come to that in a little bit later. And I finished that degree, my master's degree. Now this was a challenge. There was 7 of us on the course. I was the only male on the course. I managed really well to get through that. And a very dashing Dr. Mincher was the program leader. And this was the first master's outing for our drug design and biomedical sciences course. So that really made me think about actually how compounds and drugs interact with biology. And that was the start of the interest. Then came the PhD, and that was at Napier. And that was something that was inspired by, again, Dr. Vicky Stone, who was becoming a bit of a leader in her field round about particles and air pollution. And she offered me a PhD studentship supported by this man here, Professor Ken Donaldson. Now, for those that don't know Ken in the area of particles, he was the godfather of particles working in Edinburgh, and actually working with Ken and Vicky and others really put you on the map as an early student, and it was really important to be working with his team. And I met other people that influenced me at this point. Peter Barlow, who's in the audience tonight. Peter and I started our PhD at the same time. I did my PhD in particles with Vicky, and he started his with Anna. I also met this young man at the side here, who's now a professor at Portsmouth, Alex Ford, who is an ecotoxicologist. Lindsay Ramage was an important part of that journey as well. And Dr. Eva Malone, who's also in the audience tonight. Eva joined 1 year into my PhD, and she had the unfortunate nature of me becoming her mentor in her first year. And together, we've bonded, and well, we've bonded, and we've supported each other through our academic journeys and careers. And then this man was I would say, the expert in the field, in the lab, Dr. David Brown. He was somebody who knew everything to support our academic journey. He knew all the lab skills. He knew everything that you needed to know about running a laboratory. He also had a very predictive nature, I think. He knew more than probably most. I don't know if anyone could read that on his forehead there, but it says Laura Hart Gary. And so that technician who's sitting at the front, we became engaged, and happiest days of my life started. Now, Laura was a technician who was doing really well academically and was following a path of her own in research. And we set off very well together, and have been together ever since. And for those that know me very well, they recognise I'm always in a suit and tie. I don't still wear the love beads that are underneath there, but that was me in my younger days. And my parents were the big supporters. I think this picture shows how happy they were that I had actually found somebody, and somebody had found me and taken me off of their care. But they were really supportive of me during this time, during my PhD. So, the PhD was on air pollution, and it was on particles. And what I want to do is go back again, reflecting on history. What we know about air pollution in particular is that it's been a growing problem since the 1800s because of the Industrial Revolution. So we've seen the tonnage of carbon particles and air pollution increasing hugely up to the point of the 1950s, where the Great London Smog Incident took place. And that caused real harm to the population of London with severe casualties and hospital admissions. And it was this 1952 fog episode that actually stimulated the government to create the Clean Air Act. And that Clean Air Act comprehensively changed the way that Britain dealt with air pollution. And this graph here in the blue shows if we were to undo that Clean Air Act, the number of hospital admissions would rise by over 200%. And the number of deaths associated in the country would rise by over 20%. So this was a really important piece of legislation, and it was all about controlling particulate matter in the air. Now, the work of Ken Donaldson and others was out of a period of time where we knew about particles and we knew about the effect of materials interacting with our respiratory system and our lungs. Now, the IOM, the Institute of Occupational Medicine, which is still operating at full steam, has done a lot of work working with the Coal Board. They were actually born out of the Coal Board as a research institute, looking at the effect of particulate and coal and silica on occupational exposure in miners. And what they showed there was that the size and shape of the material, the actual material itself, could elicit what you notice as miner's lung. So you would have blackening of the lung, damage of the lung, which could lead to chronic respiratory problems. So the data was building there around about how these materials could cause harm, and actually a lot of the material that they were looking at related to what we found in tobacco smoke. So you can see that this linkage started to grow in evidence. In the USA, there was almost a perfect laboratory set up in Salt Lake City in a valley. Now, it's very rare for people to have a live experiment go on. And what happened in Salt Lake City, this is a valley basin where pollution couldn't escape when there was an inversion of weather. And there was industrial action, which closed a steel plant in the city for almost a year, over a year. And what this epidemiologist, Ardent Pope, looked into was the association between hospital admissions and health. And what he found during that period when the steel plant was closed, hospital admissions and death rates fell dramatically. And then when they switched it back on, they started to increase again. So this was a lovely, dreadful, but lovely experiment that actually proved that air pollution was directly correlating with hospital admissions for children. It was related to respiratory problems and also cardiovascular problems. This was the basis of my PhD. This was the thought process, and the Department of Health and DEFRA spoke with my supervisors, Vicky and Ken, to come up with a plan. And a same project actually occurred here in the UK, and this is in the northeast of England in a town called Redcar. Now you can see on the map here that it's quite an industrial part of the world. There is a large blast furnace here, which was producing 3.6 million tons of iron per year. This used to be run by Chorus Steelworks. And there was a range of other kind of petrochemical plants and other industries round about there. On the map, you might see the small circle at the far side, and it's the AUN site. This AUN site is where DEFRA was actually collecting air pollution samples. For my PhD, we were actually getting samples delivered to us that we could look at to see whether they had anything in them that could be toxic or not. And we got wind data just to make sure that we were actually measuring samples coming from the right sources. But what was interesting for us was to actually look at the metallic content of this particulate matter. So if you think about diesel particles, you think about soot, you think about carbon, it's black and there's lots of stuff mixed up in it. But here we know there's an industry producing metal, and we wanted to understand how much of that metal component was present in the samples. Unfortunately, we didn't get a lot of samples before the steel plant closed, and the steel plant was actually winding down, so we don't have the beautiful data that we got from Utah. But here we can see that the metal content when the steel plant was closed compared to when it reopened is significantly different. And the two bars there show the difference of total metal and metal which is soluble, which is metal that can be actually come into contact with your biological system and be dissolved, and metals which are actually solid and don't dissolve, so therefore could interact and persist. We did some further analysis. We used mass spectrometry, which is a detection technique to actually break down the elemental components. We could see there that in the top, the aqueous fraction, the big bar is white, and that's zinc. There's quite a lot of zinc in the metal content. But when you look at the insoluble fraction, most of it was iron, which is not surprising, being an ironworks. So what did that mean? Did that mean anything from a safety point of view? Well, we did some animal studies, and we started to look at what we would say an early marker of damage in the lung, and it's called the neutrophil. So for the immunologists, it's the vanguard of an inflammatory response. And what we saw when we treated a rodent model, so we put these samples into the lung, we could see that where there was a high metal content, there was a high influx of these cells, which would suggest to us inflammation and damage. Now, when you break that down to the soluble and insoluble, it was still significantly having an effect. Now, that's really important because now we're starting to understand that the metals in the air pollution could also be exacerbating or driving some of these problems. But to prove that, what we did was a fancy experiment to strip out the metal. So what we did is we took out the iron content and then we put that back into our test system. We call it calyx. And you can see here at the far right, when we actually used the calyx, we took out the iron content and the bar dropped, which means we could prove that the iron was actually driving some of this inflammatory response. This was really interesting, and I had to go down to meet with the board at Chorus, go in and present my data to them, which was very nervous as a PhD student going in front of a steel company board to say this is what's happening. And they sat and they listened, and I said my piece, and at the end they went, "Thank you very much." Looked and they said, "We kind of expected you were going to say something like that." And that was it. So it was a known quantity, but for the government it was helpful data. So that data went to the Department of Health and to DEFRA to help them with their air pollution planning. At the same time, Peter was doing his PhD looking at particles, and the two of us were working in tandem. And at that point in the laboratory, we were sometimes called Bert and Ernie. And I will leave you to decide which one is Bert and which one's Ernie. But a few months ago, I got a message from Peter, and he said, "It's great we're still working together, but we're no longer Bert and Ernie. We're probably more like Waldorf and Statler in the Muppets." But we've been together for quite some time, and Peter's gone off to the USA and worked on a range of different projects, but we've still shared some common interests in particular in air pollution. And we graduated. So the PhD was a success, it was defended, and that was the end of that part of the story. I'm going to come back to the history of particles and air pollution, but in my journey through toxicology, I left Napier and I went to work, as Andrea said, the Medical Research Council down at the University of Edinburgh. And just in case you think my pathway is planned, nothing's planned, and things happen. And I went off to work for this gentleman here on the right, Dr. Gerald Lincoln, who sadly passed a few years ago. And I went to work on a project that he had funded by the MRC looking at circadian biology, so the clock in our brain which responds to light. And the model we used was a sheep model. It's called the Soy sheep, and it was found in the Isle of St Kilda, which means it's not been affected by light pollution. So really, really good model for measuring the clock. Now, if you think about it, as a PhD student, I spent my time in a white coat. I spent it in a sterile environment working with particles. Here, I was taught how to catch sheep. and I was taught how to hold them, and I was taught how to lasso a cow. So completely different skill set. And I thought, is this really for me? And then one night, I was in a barn taking blood from a cannula in I don't know how many sheep's necks, and I couldn't turn on the lights because that would affect the clock. And for 24 hours, I was standing there taking blood samples in the dark thinking, what am I doing? The project was fascinating, very good. I don't think it was a reflection on the project, but the MRC closed that project down, and that caused me a problem because I had signed up for a career development fellowship with the MRC, and I wanted that support and development. And this man here on the top left, Professor Alan McNeely, was a bit of a saviour. He was the deputy director of the MRC Centre, and he introduced me to this man here, Professor Richard Sharp, who, again, like Professor Ken Donaldson, was a world leader in his field, and I was so fortunate to have the opportunity to work with Richard. And his team of clinicians, so Rod on the left there and Amanda at the top, were doing their medical doctorates, and then the team here of PhD students and other staff, just a fantastic group of people to work with. And he was interested in looking at how chemicals could be used to model diseases that occur during fetal development. So it was a step back into reproductive toxicology. But Richard taught me a valuable lesson. Never overstate your data. Always think about your data from all angles. And he was very thoughtful and very understated. And I learned a lot from working with Richard because he taught me some very, very good science. I spent 3 years with Richard, and his interests were actually looking at male reproductive disorders. And this data here is the formation of the thought process round about this. Here you can see, based on the decade you were born as a man, your sperm quality and sperm number is decreasing. This was a concern. This, backed up with data sets captured from different regions of Europe, started to point to the fact that where there were low sperm quality and quantity, and predominantly in Denmark, the male population there had a higher incidence of testes germ cell cancer. They started to think, are these things linked? And again, if you see the Finnish data, healthy sperm quality, content, low incidence of germ cell cancer. So a phrase was coined, testicular dysgenesis syndrome. And this was thought to encapsulate all of these disorders. And what we have here is the 4 disorders on this cartoon. So in the yellow writing at the side, you've got the testes germ cell cancer and low sperm count. And that only presents in early adulthood. Okay, you can't detect that before then. But there are disorders that were picked up by clinicians right when the baby's born. And they are hypospadias and a cryptorchidism. A cryptorchidism is where the testes fails to descend into the scrotum. And it can happen either side, both. Hypospadias is something that's very hard to correct. It's where the urethra opens not at the tip of the penile shaft, it opens on the side. So, quite debilitating and really difficult. So the clinicians have to actually correct that through surgery. All of these were thought to have a common origin in fetal life. And the data from epidemiology was pointing towards that. So what Richard and his team did, and I was part of that, was to try and create a model, a toxicology model, that could be tested to see whether they could understand the adverse outcome pathway, it's what we would call, of how these disorders happened, what molecular switches were switched on, which cells were targeted. And it's really interesting, it only happens in baby boys. So here we see that in very early stages of embryogenesis during pregnancy, at week 7, a switch is activated. So if the baby is a boy with XY, there's a region on the Y chromosome which switches on a whole lot of cells in the gonad, and it turns it into a male gonad. It's very clever. And what happens there is that process is very much driven by hormones. If that switch doesn't go on, the master plan is the female. So sorry, men in the room, master plan is female, men only if we get switched on, and we're very, very reliant on hormones making us work correctly. So I think there's a bit of an irony in this somewhere. But what that means is there's a window of susceptibility, which means that if hormones are disrupted at this very early point, something could go wrong. So everyone's heard of endocrine disruptors. What we were trying to see here is there chemicals that we're exposed to in the environment that are interfering with this stage? There are a number of cells at the very early stages of the testes being formed. The Sertoli cell, and it's absolutely essential for creating the testis structure, during fetal life. When you get into adult life, it's the cell which allows spermatogenesis to occur. Male sex hormone is produced by a cell called the Leydig cells, and it sits outside that structure. I'm telling you that because these are the things that have become interesting to me as targets. But to test the model, we had to find a chemical, and the chemical that was used is something called a phthalate ester, and it's found everywhere. It's really a very clever chemical. It's used in everyday modern life, and it really transforms the way we do things. It's absolutely essential in tubing, for example, neonatal blood bags and such. So it's really changed the way we live. As a chemical, we know it crosses the placenta. So the mother can be exposed to it, it can cross the placenta, and we know it comes out in the urine. So it doesn't stay in the body, it passes through it. But what we wanted to do, a lot of reproductive toxicology is based on animal models. So we had an animal model which we exposed to quite high levels of the phthalate, the chemical, and that's because a toxicologist should be using quite high doses to try and reduce the number of animals needed in tests. So it's artificial. So what I'm telling you here isn't something you should be worried about. It's just to prove a point more than anything else. But what we did was expose the pregnant mother, the rat, to the chemical during the pregnancy, and then we looked at different stages of development to see what happened to the testes, and then what happened to the testes and the pups that grew up to become adults. In the model, we could prove all the endpoints apart from germ cell cancer. We couldn't prove that one, and there might be reasons for that if you think about the length of time a rat lives for and whether we can pick up early stages of cancer. What we did detect is changes. So here we've got an adult control. So this is a histological section. So we've cut through the testes and we're looking at a slice of it, and it looks like spaghetti. So that's normal. When the chemical has gone through the mother and it's affecting the pup, you get areas that don't look normal. They actually look all broken up, which is something we call a dysgenetic area. It's damaged. What we could see here is that there was something that the chemical was doing that was allowing normal development of tubules and areas that are not normal development to happen. So what was causing that? And it was all about trying to understand how the chemical was targeting this. So the first experiments that were done were trying to see whether it was a delay in development, something was going wrong. Here we can see across the bottom axis here, the time that during pregnancy. So a rat stays in its mum, keep saying a mum, inside the dam for 21 days. So this is the last week of pregnancy. And the chemicals present, what we see is the cells that are the germ cells, these are the cells that will eventually become sperm. At this point, they are like stem cells. They keep dividing uncontrollably, but then they switch off because they reach their final status. And the chemicals present, that switch off doesn't happen quite so abruptly, so something's keeping them going, which suggests there's maybe a delay happening there. So the chemical's doing something. We started to look, and this is a nice colourful slide, but this is antibody staining looking at proteins. And what you can see here, if I point this part here, which is like a black mass, you can see the germ cells are actually clumped together. And what we think is happening is there's not enough Sertoli cells, the green ones on the outside, to actually interact with them to pull them apart. So there's something happening that's delaying that as well. We did a count, we had a look, and when the chemical was present, yes, there were less of these Sertoli cells present. So something was slowing them down, something was stopping them from acting. Why is that important? Well, we know that the number of Sertoli cells that a man has is directly linearly aligned to the sperm that can be produced. So if you've got less Sertoli cells, you will have less sperm production. Here we were starting to pull together pieces of evidence that might help the scientists understand how these diseases were happening in real life. We also looked at Leydig cells. So these are the cells that produce the male sex hormone, testosterone. What you can see here in the yellow bars is the chemical. And whenever the chemical is present during the fetal development stages, there's less. So what it's doing is it's not only reducing the Sertoli cell, it's reducing the Leydig cell. But why is that important? That's important because it's also reducing the amount of testosterone that's being produced by these cells as well. We're starting to see a reduction, we're seeing a delay, we're seeing something change. Why is that important? Well, if you look at the pathway for a baby to develop, testosterone is really important for that to occur. Now, we've got a window where development happens, but if the phthalate, the DBP, is actually pushing that window off to the side, are we actually stopping normal development occurring? Now, all of this is internal. How can you tell? If you're a mother and you're trying to wonder if your child has got any potential long-term effects that you won't know until they're an adult, is there any way you can detect that? And Shanna Swan, who was an epidemiologist in the USA, did a study measuring the distance between the anus and the genitalia. And this was one of these interesting facts that you get that you don't read anywhere else, but who knew that the anogenital distance for a boy is bigger than it is for a girl on average? Okay, it's 1.5 times bigger. That's important because what we wanted to do was see whether we could predict all these internal changes externally. So to do that, we used another chemical. This chemical, flutamide, is used in prostate cancer treatment, and what it does is it stops androgen action, the testosterone. It stops it from working. So we think testosterone is the key. When we gave our pregnant models the testosterone at this late stage, when the male coiling and structures start to form, it had no effect. So we developed a male anogenital distance. Well, everything else appeared as normal. But when we gave the blocker to testosterone earlier, it caused a female anogenital distance. So something had changed. Pups had hypospadias, so the penile shaft hadn't developed correctly either. There was no prostate in these males, and they had reduced penile length and cryptorchid testes. So now we've got a window of exposure, we've got a mode of action where the chemical potentially has an effect, and that made us think, well, we now have an understanding of areas of susceptibility. What Richard always said to me is, let's not scare people because pregnant women have enough to deal with. This is a model, it's a high dose exposure of a chemical. His advice was, if you are concerned about these things, you should try and let your partner paint the room, prepare the nursery, try and stay away from things wherever possible, but please don't be concerned because they're a modern chemical. And of course, this is only one chemical. We're exposed to lots and lots of chemicals. So, I left the MRC at that point. It was fascinating. I learned a lot about reproductive targets. I learned a lot about toxicology. And I was thinking, what happens next? And at this point, going back to my air pollution days, nanotechnology was blossoming as a new technology. And it was all based on particulate, which is similar to air pollution. Very small, nano-sized materials. Loads of reports coming out, and I thought, well, I wonder if these kind of chemicals are the kind of chemicals that perhaps could interfere with what I've seen in the reproductive system. I suppose you have to understand what nano is. And I think the best way to think about it, because there's lots of technical terms, but if you think about clever engineers who can create something at the nano size range, it's taking something equivalent from the Earth. So if you imagine the football is equivalent to the Earth, then the nano size range of particulates in engineering is fold change again down from that. So it's quite a distance in actually size. Why is it important? Why do engineers want to create things at this size? Well, as you take something of a mass, let's just say it's 1 gram, if you take that 1 gram and turn it into a smaller size range, a nano size range, you increase the surface area. So the weight stays the same, but the surface area becomes huge. And that's really important from an engineering point of view, if you're looking at electrical conductance, so you're looking at absorption of drugs, and you end up with a huge amount of interaction. Now, from a toxicologist point of view, that means that chemical now has much greater surface area to bounce into a biological system. So therefore, this thought process was, what do these nano things do, and how do they actually interfere with our biology? Why do they want to do it? Well, here's an example. There's gold as we would recognize it. When you grind it down to a microgram size, it stays yellow. But when it goes into the nano size range, yellow gold changes color. And you can see all the colors of the gold there. So we've got violets and pinks. So by playing around with the size of something, you can change what it does and how it looks. So it's really interesting from an industry point of view. From a biology point of view, it causes a bit of concern. And they're everywhere. So again, this is not to scare everybody today, but these things are in products that actually are enhancing our lives as well. This slide's just to show that size is one of the complex things that you've got to be concerned about with nano. There are a huge number of things that we have to consider when working with them, how soluble they are, what their charge is. So from a toxicologist's point of view, there are so many variables in there that you have to think about when interacting with biology. So this led me back to Napier, as I said, and Vicky at the top said, Gary, there's lectureships coming up at Napier. I think you should apply for it. And I did. And this gentleman here, Mick, who's in the audience, worked at the MRC unit at the other end of the room from me. And we both started at the same time on the 1st of September. Mick, an expert in female reproductive biology, me, someone who did air pollution, who was doing some male reproductive biology, and we came as a team. And at that point, I was trying to get people to think about reproductive toxicology and nano and not getting a lot of traction. Eva, who had left the university, taken other roles, had come back to the university, and Eva and I took up where we left and started to think about how we could look at toxicology and look at some of the things. And we wrote this book here to try and persuade people to think about reproductive biology as a target. At the point, nobody was giving me money, nobody was interested. Particles were a lung problem or they were a liver problem, not a reproductive problem. So I wasn't getting much traction, I wasn't getting much money, but I still think it was of an interesting thing to do. And Eva was with me. God love you, Eva. You stayed with me for quite some time on this one. But reproductive toxicology is really complicated because there are so many endpoints you have to think about. You've got the male and you've got the female. You've got the targets in the ovary, targets in the testes. You've got development, you've got fetus. It's so complicated. I had to start somewhere, and I thought, let's go back to the target cells that we looked at when we did the work with Richard. And we thought about the Sertoli cell, and we thought about the Leydig cell. And that's what we plan to do some work on. Bryony, who's in the audience, PhD student, we tried to get some movement in the field, try and get people to think about this as an important topic to look at. And with a team of scientists across Europe, we wrote a paper to try and highlight that nanoparticles could be a potential reproductive toxicant. And we did it from an inhaled point of view, inhaled particles. Still wasn't getting much traction. We kept persevering. But the models which I talked about with Richard, with Vicky, were really important to me because toxicology is all about the modeling. And working with Vicky and people at GSK, the pharmaceutical company, David Hassel, they approached us to say, we know you've done quite a lot of work in particles. We know that you understand how they interact with the body. We're having real problems at GSK because we're producing asthma drugs and they keep on flaring up hazard signs and we don't quite know why. And we helped them to understand it was sometimes the size or the shape of the particle, so that physical-chemical circle that I showed. And what we did is we helped them reduce the amount of animals that they required in testing. So we developed a cell-based model, and Anton Vessels here was the postdoc that helped with that. And that cell-based model actually saved GSK £7 million a year because they didn't have to do so much work with primary dog work. I don't think it sped up drug discovery, but from their point of view, it was a huge cost saver. And for us as an institution, it was really important to show our science had an impact on drug design. That was a fascinating project, and I learned a lot about the pharmaceutical industry. Dr. Jenny Fraser came to work with us, a postdoc, and Jenny and I did some really interesting work again, trying to think about how you could manipulate these small particles. And we thought, could we use them in a reproductive setting again to prove the principle that actually they do get there? And what we did was we did a piece of work, and Jenny, to be fair, did the lab work, actually started to bind antibodies to the particles to see whether we could get that really clever small particle into parts of the body to enhance detection. So if you think about it, when you go to the hospital, you get screening, MRI screening and all the rest. Some very small proteins are really hard to detect. And what this clinician wanted done was detection inside a pregnant animal and inside the brain of the pup. So You can imagine very low quantities of protein and a pup's moving around. So trying to get an image on a screen was really difficult. So we proved that you could put the antibody together, you could measure the protein, and it didn't do any harm to the pup. It was a really fascinating story, and that was us trying to look at how these things could be used as a nanomedicine. I then went down to London. Okay, I'm getting told to hurry up. Went down to London, and I spent some time working with policy and practice, and it was really important doing this work. It's influenced a range of different thought processes for me and what I do. If you think about chemicals, and you think about all these nanos, and you think about everything, this was the kind of graphical chemical production from the 40s. In 2050, this is what's anticipated, the amount of chemicals that are going to be produced. And if you think about the particles and all these things that are going to be coming out there, all the tests that have to be developed to make sure they're safe, there's quite a lot of work to be done. But what people don't often think about, because pollution is the unseen quantity, pollution actually kills more people than a range of other endpoints, such as AIDS, smoking, alcohol use. So it is a massive problem that we have to address. It's more prevalent in causing deaths in low-income, middle-income countries. So that's because the regulations may be a bit further behind Western countries. But it's the unseen part of the planetary boundaries discussion. People know about global warming, people know about acidification, but these novel compounds, less is known about. So, working with DEFRA, we wrote some papers. This was me. I keep saying we. Wrote some papers working with people, and I can see Leslie's in the audience, who was with me on the Hazardous Substance Advisory Committee, to try and inform the policy thinking round about how to deal with these chemicals. And that was a really interesting insight to me, because understanding how you as a scientist at the bench can actually do something to inform policy was a real learning curve. And we produced a paper which was to help the government improve the development of chemicals. And it was to try and improve the design and the development of the chemicals in a safer manner than had been done in the past. So that was published, really trying to push that safe and sustainable by design. And that mantra is now coming out through industry across Europe. So it's really important, and it was good to be part of that conversation. Finally got some money. I got some money to do what I wanted to do. And doing work in reproductive toxicology, as I mentioned, uses a lot of animals. And we wanted to come up with another way of doing it. And that was going back to look at cell-based models. These cells along the bottom are our Sertoli cells in a tissue culture flask. So grown outside the animal, grown in a lab. And here you can see the black dots is our nanoparticles. What they do is, over time, they actually go into the cell and they sort of locate in different parts of the cell. Here, this electron micrograph image, just on this side here, shows almost the cell engulfing it and taking the particle up. There's an active uptake of particles as well. I've had very talented PhD students, Bryony, Dr. Ross is in the audience tonight, up in the top right, and Sarah, who's just finishing her PhD, both working with the support of Mick and Eva and Leslie, who have been working on this program through European funding for a long time, a long, long time. And what we were interested in and looking at is how these particles could interfere with these cells. So the first project was Bryony's project, and we were looking at engineered materials, the stuff that people were producing that was going into products. And we worked with a number of European labs across Europe, funnily enough. We were all looking at different parts of the body to see whether the particles could be tested to see whether they were harmful or not. What was fascinating is that we could prove that the particles were toxic in every single cell type the same way. It was the particle that was driving the effect rather than the cell type's response to them, with a few exceptions. So that's really important, because if you think about all the test systems you have to look at in the body, if you can say that actually this particle is hazardous, that helps the designer come up with a more safe and sustainable way of doing it. Bryony, I gave her a horrible challenge, because as toxicologists, we're not reproductive biologists, and I said to Bryony, it'd be really good if we could actually assess the effects on sperm production and spermatogenesis. And Bryony developed a really nice assay and taught herself how to do spermatics testing and staging, which was a huge undertaking. And what she was able to do through different readouts was actually predict different stages of spermatogenesis, But rather than to be an expert in looking at all the different stages of histology, did it through a chemical marker. That was really important, and that's something we're going to write up because we think that could be a quick way for people to do an assessment. Working with Hans Baumeister, who was our collaborator who gave us the tissue, we started to look at the effect of the particles on the adult Sertoli cell to see what impact there was on sperm. And a pathologist did a scoring for us as well, which backed up what Bryony was seeing in some of her data, because we could see that some of these particles were actually causing effects on sperm development and sperm production and changes in where the sperm should be in the cycle. That was a really big piece of work, and I've not done Bryony justice by covering her PhD in 2 slides. But we've moved on quite dramatically into the next step of that work, looking at bionanomaterials. And Sarah's been looking at the similar types of assays to see whether there is an effect on the Leydig cells, the Sertoli cells, and now the ovary to see if there was any impact there. But what we see is a similar profile to what Bryony showed, but we saw a problem. When we tried to back up our assays, which were a one-cell assay with another assay, it gave us opposite readings. And why was that? And it's because these particles are a real pain in the bum to work with because they don't dissolve in liquid and they absorb proteins and they mask things. They're just a nightmare. You wouldn't want to work with them, really. So what Sarah did was she saw an assay that was developed by the European Commission to look at a different way of assessing particle toxicity. And it was a cell-based assay looking at the wells of a cell. And what she showed is actually that was more sensitive and actually quite similar to what we had seen with the assay that Bryony and Sarah had used previously. We've kind of discounted this LDH assay on the left because we don't think it's good for measuring cytotoxicity. Again, toxicologist assay development work. We'll skip over that one. What we wanted to do is not just look at killing things, because that's a bit dull, really. There's only so many times you can kill a cell. But we wanted to look at low concentrations, so things that people in this room would be exposed to, and see whether it had an effect on the physiology. So we started to look at the molecular switches and levers in the Sertoli cell that controlled sperm. We did this with support of Luisa, who's out in Rome and the University of Tor Vergata, who provided us with samples. And what Sarah did here was did an analysis of all the molecular switches of that spermatic cycle. And I'm going to use my arms here just to show what this meant. So if you think about the sperm cell as an early germ cell, it starts off here. And it's got to go through a maturation piece to become sperm. And as it does that, the Sertoli cell opens and closes, and it allows the sperm cell to actually move up and mature. So all these switches and levers actually allow the cell to move up and mature. So we wanted to see if the particles actually affected that process and therefore could affect sperm. There's a lot of data in here, but what I wanted to show you is we have shown that particles at very, very low concentrations, so what we would call an inhibitory concentration of growth, so where 50% of the cells don't survive, we've been looking down at inhibitory concentrations of 10 or 5% of those cells, really, really low doses. And here we can see molecular changes. We've backed that up with protein, which is on the surface of the cells, to prove that actually it isn't just a molecular thing, it is actually a real thing that we can measure. What's fascinating here is that we can see changes, and that gives me a bit of a concern that low-level concentration exposure to these materials might be doing something that could be exacerbating what we're seeing in the male population around about fertility rate. In the middle there, we started to look at the receptors for hormones, because remember I said testosterone was really key, and the signaling pathway for testosterone through the androgen receptor was something we were looking at. This is just a slide here, which I won't go through because I'm short of time, but this is just another material which shows the same thing. So for me, this is quite exciting because now I'm starting to see molecular changes that could actually change the biology and at very, very low concentrations. So that continues. Sarah's writing her thesis at the moment, and we will be thinking about where we go with that for future work and future funding. But like every good journey, you do double back on yourself. And air pollution's popped back up in the national psyche, and across the world, everyone's talking about air pollution. And with Fiona at the top there, Dr. Fiona Kerr and Dr. Amy Poole, and Eva, the long-suffering Eva, who's still continuing on this journey, each of them have got such good talents that I'm piggybacking my interest in particles and toxicology onto their skill set and their models. And here, with the support of Derek and Maureen Moss, Beatrice completed a master's by research looking at the impact of particulate air pollution surrogates, so the types of things we'd be exposed to, on the brain. So another barrier. So we're looking at neurodegeneration. What are the cell types in the brain that could be activated, that could actually start a pathway of neurodegeneration that could lead to problems in later life? Really interesting piece of work. Like the blood-testis barrier, which is a protected area, the blood-brain barrier is the same. These tiny wee particles can get across them. So if they can get across them, what do they do when they get there? So it's a really interesting piece of work, and it's something that I know Beatrice has really impressed Derek about, who's photographed here, and he's really wanted to support that work in the future. Remember I said I couldn't get any traction. Nobody was listening to me. I was probably 10 years too early. Mick has introduced me to Professor Paul Fowler at Aberdeen University, and he's produced a study that was in The Lancet. And you'll see this perhaps through BBC News, that particulate air pollution particles are now being shown to cross the placenta and get to the fetus. So we've now got evidence that it is a real thing, and actually what impact does that have on baby and the placenta during the early stages of life, but then what are the lasting effects on that child as they develop through later life as well. Lorna's here, who's the expert in immunology, who probably know much more than me about this, but is there any lasting effect when I think about programming and such? And of course, this was stimulated by Professor Stephen Holgate, who was a scientific advisor to an inquiry led by a coroner down in London, and he said that the death of Ella here was actually attributed to particulate air pollution. That was the cause of death, and it was the first time in the UK that a cause of death had been actually attributed to air pollution. A really important finding. Stephen, a lovely man, was the chair of my Hazardous Substance Advisory Committee, so I've learned a lot from him, and I've been very lucky to be touched, one word, come into contact with good people who have informed my way of thinking as well. But you'll be glad I've almost finished, people. I'm really sorry I'm taking a bit longer. What I wanted to say is what happens next in all of this, and where do I go? Because I might look a bit grey, but I'm still got a few years left in me yet to do some work. The OECD has kept, which is the organisation that looks at all the tests and all the models for toxicologists to look at, they've constantly reported there are so many improvements required around about the safe management of these materials. The strategies and the testings and exposures need to be consistently refined. We've got an approach, it's dated, it doesn't work for the future. Where we want to get to is something that's a bit more high throughput, a bit more strategic, and again, part of Bryony's PhD was to think about an intelligent testing strategy, a way of piecing together all the bits of the jigsaw to help you come up with a hazard assessment. Why is that important? Well, because there's another thing on the horizon. Particles are just the start, and nanotechnology is just the start. In Europe, I attended a number of meetings for the government looking at the advent of the advanced material. And this is a material that's using biologics, it's using nano, it's using synthetic, it's using all sorts of complex materials and putting them together for a function. And that's causing regulators and toxicologists a bit of a headache, because how do you break it down and how do you assess it? So this is the future, and this is what's going to keep us probably quite busy in this space for quite some time. So I've come to the end. You'll be glad to know. Thank you for your patience and letting me talk through my journey. I have secured funding for a number of years. I've been very successful in getting European funding for a number of years, and that's been so important to allow the work to happen. And I didn't want to put names up here because there are so many people that I need to thank, and I would miss somebody off that list. But for everyone in the audience who's been part of my career, I say thank you. And for those that couldn't be here today, they know that I'm very appreciative of that. I will say thank you to this lady. I'm getting a wobbly. Laura's been with me right from the very beginning. She saw something in me which I don't think I saw myself, and she, I think, sacrificed her own PhD as well to support us as a family. And actually, without her continued support and her good guidance, I don't think I would be standing here today doing this job. And it's really testament to her and her belief, I think, and these two. My beautiful daughters, who I make sure I'm at home and we have dinner together every night and we spend time together, and they keep me real because it's dangerous to work in academia and not be kept real. So I just want to say a huge thank you to my family for supporting me through my journey. Thank you very much. Thank you. My hands are shaking.
Well, thank you, Gary. That was absolutely a wonderful story, can I say? It's just a perfect entrance, a middle, a beginning, a middle. It's not an end yet, and thank you for so eloquently describing really complex challenges that we have as a society to face as we advance technologically. Now, I don't have a watch on me, but I know we will have some questions. Colleagues, would you like to kick off with any questions?
Hello, just a member of the public. Will the pending bonfire of European regulations affect UK toxicology safeguards?
That's an excellent question. So I'm not talking as a member of the government's advisory team just now, I'll talk of my own personal view. I think there are challenges because as we come out of the European family, we relied quite heavily on ECHA, which was the European Chemicals Agency, and they had a huge network of databases and information that we shared really well, actually, as a scientific community, and we supported each other. Britain is a bit of a powerhouse anyway, feeding into that conversation. I think what we're seeing now is a challenge in our regulatory bodies being built up to cope with the amount of checks. So, for example, the Food Standards Agency, which I'm working with at the moment now, is actually building that scientific knowledge and bringing in people to help them make decisions on chemicals. So I think my impression is that hazard assessment has been important for us in the UK, but we've always taken a risk-based approach. So we've looked at exposure, which is really important. In Europe, I would say it was very much a hazard-based approach, a bit less concerned about exposure. So if something was toxic, you banned it, where there was a bit more pragmatism here. I don't think it should be something we should be worried about. If I was going to be worried, I would be worried about the toxicologists that are coming through to do this work in the future, because there isn't many degrees pushing toxicologists out. And I think the good people, and some are in this room who are championing that agenda, are actually making sure that we don't lose some of the good work that's been done at Europe. I hope that answers that. Oh, gosh. You know, it's a really good question, Gordon. If I was looking back, there were so many points where I could have been cautious. I think one of them was a conversation I had with Andrea when I was offered the head of schools job. And you said to me, please don't respond immediately because your research is going this direction. This job could take you away from that. And I thought, it could. But I took the risk and I went for it. And I think what I would say to that person back then, who, as you could see, wasn't a bit of a looker compared to the other people in the photographs, there was a confidence issue. I still, until probably quite recently, suffered with confidence. And I think if I was going back to say, don't be too harsh on yourself. And if you want to try something, don't judge yourself by what you think other people are looking at you or saying. And I found that even with committee meetings, I'm looking at Leslie, joining these committees with eminent professors, eminent people, and you sit quietly and then you think, actually, I do have something to say. And then when you say it, people listen and you think, I should be more confident in myself. So to anybody who's thinking about starting a career, have some self-belief, because I've not always had it, and I've had people to help me in this corner here with that. Thanks, Gordon.
I've got a question, Gary, because I suppose I came into the lecture ignorant of all the hazards around me. And I just thought, you know, as you went through, and I thought, Well, the phthalate, story was very high levels, but then as you started to look lower and lower, so who sets minimum thresholds, and is there a minimum threshold? And yet nanoparticles are everywhere, part of our every life in existence. We would lose so much, we just can't go back. So who sets the thresholds, and where do we, I mean, you said where we go in terms of testing, but in terms of that societal awareness and that risk-based approach?
It's a really good question. The difficulty with setting the thresholds for risk around about exposure is dependent on what it's being used in. So if you were using nanomaterials and they get used in food packaging. So if you think about preserving your food and keeping it longer on the shelf, there's nanotechnology in that food packaging. So that falls under the remit of one authority, so food standards is an example. From an occupational, it could be the health and safety executive. And therefore, there are different regulatory bodies looking at these exposures. With nano, it gets even more complicated. And Leslie will probably laugh because we remember sitting looking at a paper at DEFRA where the European Commission was trying to come up with a definition for nano to help with that mapping of exposure. And you could have, I think it was a tennis racket. And if over a certain percentage, if it was made with nanomaterials, that tennis racket was therefore classed as a nanomaterial. Which is a bit absurd because you're not going to inhale a tennis racket, but it's therefore round about what happens with the breaking down of the substance at the end of its life. So I don't think there's anybody definitively looking at this, but when it comes to occupational exposure, the likes of the Institute of Occupational Medicine will work with the Health and Safety Executive to look at normal pollution levels in a work environment to keep us safe. It's a moving feast.
Clearly, lots of work to be done. Any other questions? One more here.
What's your favourite part of your job?
Was this a really good question? You know, the favourite part of my job is asking a question and then trying to work out how to answer it. And do you know, if you ever done a game where you've been like an explorer? You know, I often think of myself sometimes as not a very cool explorer, not like an Indiana Jones, but somebody who wants to find out how to get an answer. And therefore, you've got to find the people that are going to be on your team. You've got to find the best tools to answer the question. And that, to me, is the fun part. It's the writing up part that's a bit dull. And that's where your mum sitting beside you was an absolute wizard when we worked together on writing, because your mum had an absolute talent in keeping me grounded when it came to writing. A great question. Thank you.
Thank you. Okay, I'm getting signs that we're coming to the end. Gary, I didn't realise we share something else in common apart from being leaders at Edinburgh Napier. Was my PhD, I was lassoing sheep all the time, turning them over, sheep with foot rot, but anyway.
I've never used that skill again.
You never know when you might need it. Thank you so much for your professorial lecture, for a fascinating journey around toxicology. Really, really enjoyable, made the whole subject area so interesting and so accessible. Certainly for me, and I think for everybody in the audience. I hope so anyway. So thank you again.
Thank you, Andrea.
Before I just invite you all to join us for some drinks and some nibbles downstairs where you came in, I'd like to thank Nicole, Miriam, and who's at the back, and Michael, who organised this evening's lecture. You know, these things a lot of work goes on behind the scenes, so thank you very much.
Can I just say one thing? I
Yes,
forgot one
you
person. There's one person in this room that I didn't mention in my slides, and I forgot to put the picture up, and it's to thank Susan. Susan is in the audience, and Susan is...
there she is.
Susan's Susan works with me and keeps me right. Some people think Susan is the dean of the school, actually. to maintain research and try to be dean is really difficult, and Susan is a huge part of that, and she did a fantastic job, Susan, so I just want to say thank you for it. Thank you, Andrea.
Okay, so on that note, I'll invite you all to join us downstairs, and thank you for your attendance here this evening. Thank you. Thank you.